Hey there, Chem Squad. In today's class, we're going to look at orbital box diagrams. All right, so orbital box diagrams are based on three principles or rules. The rules are listed out at the bottom here. So we have the Aufbau principle, Pauli's exclusion principle, and Hund's rule. So all three of these will come into play, and I'll identify them when we actually need them. Now, you should have already gone through electron configurations at this point. So what I want to do, we'll use an electron configuration to help us get started. So let's look at fluorine. No, actually, not. Let's look at nitrogen. So if we look at nitrogen's electron configuration, and we're going to start with the expanded form, okay? You're going to start off with 1s, 2, 2s2, 2p, 3. Okay? So nitrogen has a total of 7 electrons, and through the electron configuration, we can tell which orbitals these electrons are occupying and at what principal energy level or quantum number they're at as well. Now, the whole idea of the box diagrams is to show how the electrons are filled in to these orbitals without drawing something as detailed as a quantum mechanic model. So if we understand that this is your electron configuration, what a orbital box diagram would look like would be something like this. So every orbital is represented by a box. Okay, so this could be representative of a 1s orbital. All the s orbitals are single boxes that are separated from each other like this. Okay. The p orbitals, we know from the quantum mechanic model that they look like dumbbells or infinity signs, and there are often 3 sublevels or component. But as a box diagram, we represent p orbitals like this. 3 boxes that have been merged together. Okay, so they're stuck together. This would be a p orbital, and because we're talking about the second energy level, or second quantum number, it's a 2p orbital. Now, organizing the orbitals from lower energy levels, so this is a low energy level, and this is a higher energy level. This way of organizing our orbitals is basically Aufbau's rule, or Aufbau's principle, sorry. So we'll say Aufbau principle states electrons must be filled from low energy orbitals to high energy orbitals. Okay. Because every orbital, it represents a region of space that is further away from the nucleus. So if we start with 1s as being our lowest energy level, okay, all electrons have to be filled into the 1s level first before moving on to 2s, before moving on to 2p. So the way that we represent electrons, okay, is by drawing an arrow like this. So if I have 1s1, okay, which is essentially what this is, I only have an arrow pointing either up or down, okay, it doesn't really matter, in that 1s orbital. But Pauli exclusion's principle comes into play because when we put a second electron into that orbital, like this, we have to put it in opposite directions. Okay. This is known as Pauli's exclusion principle. And it states pairs of electrons within a sublevel. Okay, so in this case, the orbitals slash components of an orbital must spin in opposite directions. Okay. So that means electrons, when they come close together, they don't attract. Because they have the same charge, okay, same charges repel each other. So to show that electrons are repelling each other within a sublevel or component of an orbital, we draw the arrows in opposite directions. So you would never see me put two electrons that are facing the same direction like this. One of these arrows has to be facing in the opposite direction. Okay, so this part makes sense. So every time you see an s orbital, okay, because they can carry two electrons, you would put two arrows in opposite directions. Okay, now once we get past the 2s, we enter the 2p's. And you'll note that we still need 3 more electrons. But the thing is, we cannot put those 3 electrons like this. This method here is incorrect. And the reason why it's incorrect is because now you have this component, this portion of an orbital, that has no electrons at all. There's an imbalance in charge. So instead, what we actually see is this process called Hund's rule. So let's just scroll down a little bit here. Hund's rule states each sublevel slash component of an orbital is filled with at least 1 electron before placing a second electron in the remaining sublevels. Okay, so each of the sublevels, so each of those boxes has to have at least one electron before placing a second electron if needed. Okay, so I'm just going to go back up to the diagram here. So what this means is I have to put an electron in each one of these sublevels, like this. This is Hund's rule, right? So a p orbital contains 3 sublevels. Okay, which I usually call components. Okay, you know them as the 2px, 2py, 2pz. Okay, those components are those portions of the orbitals that are occupying different axes on the Cartesian plane. So you put one electron in each of those orbitals first, and to note, they're all spinning in the same direction. Okay. So if I require another electron, I can put another electron into the first sublevel here, okay, but it would be pointing down. If I need another one, I'll put another one into the next one. Okay, so what I have right here, right now, this is basically nitrogen. Okay, I have 7 electrons in total, okay, represented. My 2p orbitals have 3 electrons, and it's showing where those electrons actually are. Okay, so they're placed 1 electron in each of the 3 sublevels, okay, or components. They're all pointing in the same direction. If I wanted to draw out the next atom, okay, which would be oxygen, oxygen would have an extra electron. Okay, that electron would go like this. Fluorine comes after oxygen, so it would go like this. And then finally, if I were to draw neon, it would have those 3 extra electrons. So considering that I just want nitrogen, I don't need to put those in. Okay, but if you do, then you actually have neon. Okay, so this is what we call an orbital box diagram. There are shorthands for this, okay, but there are no shortcuts. Every time that you draw a orbital box diagram, you have to start with 1s and then move your way up to the very last set of orbitals. Okay, so to summarize, and beyond. Oops. Sorry about that. Okay. A single box represents an s orbital. Okay. A set of 3 boxes represents p orbitals. What do you think the d orbitals look like? Well, d orbitals have 5 components, so that means you have 5 boxes. Like this. So this would represent a d orbital. While the F's, they have 7 components. So you have 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. 7 boxes chained together would be F orbitals. The whole point of these box diagrams is to show how these electrons are arranged and how they behave. So box diagrams are intended to show how electrons behave in neutral atoms. And these box diagrams can sometimes be used in reactions too, between different elements. We won't get into that kind of situation, but can also be used to describe ion formations, electron promotions you can use these for. Or other reactions between atoms. So we'll do one last example. Okay. Let's look at copper. At this point, you guys would have at least gone through one of the exceptions for your electron configurations, hopefully. So I'm going to use the shorthand method just to show the final set of electrons there. So this will be argon, and you have 4s and 3 ds, okay, for copper. And copper has a promotion from one of the s's to the d's. So its proper electron configuration is 4s1 3d10. Now, if you were to draw this as a box diagram, you have to start at 1s. So sometimes it actually does pay to write out the electron configuration, but we're going to have 1s, 2s, 2p, 3, oops. The next one is 3s. Okay. Okay, this one's 2p. Then you go through the 3p's, like this. Then 4s. And then you have your first set of d's, which are the 3ds. And it has 5 boxes. Okay. So once you have the orbitals in place, you need to put the electrons in. So starting with 1s, going all the way to 3d, that is Aufbau's principle. I put the first electron in for 1s. So with the s's, each s is its own component. So when I put the second electron in, I'm showing both Pauli's exclusion principle as well as Hund's rule. It's just that for Hund's, this is only one box long, so it doesn't really show as nicely as when you put the electrons into a p orbital. So we move from 1s to 2s, that's Aufbau's principle. You put the electrons in opposing direction, that is, again, Pauli's exclusion. Okay. The next one that goes in, okay, has to be in opposite directions to complete the orbital, so that's Hund's rule. Hund's rule is seen more clearly over here, where you have to put in the electrons in one of the sublevels each, and then you go back and you put in the second electrons into each of those sublevels. So if I just sped it up a bit, okay, this is how everything should look as it fills. But then we get to the 4s. So if you remember, if I were to just put in my electrons without seeing the promotion, it will look like this. It'll be 4s to 3d9. But because copper is one of the exceptions, okay, in order to make it more stable, I take one of the electrons in the s orbital and I give it to the d, so that now the 3ds have one electron in each sublevel, and it is pretty much balanced. Okay, even though they're half full only, they are a little bit more stable than when this particular electron was missing and you have a vacant sublevel. So here we have our 4s1. Oops, this should be 3d5, my mistake. So some of you guys probably have noticed that. If you didn't notice, then that's too bad, but I didn't notice either, so it's all good. So, oh, sorry, no, that was right. What am I talking about? I'm just not finished, is all. Copper is 4s1 3d10. I just needed to put the other electrons in here before I promote. Okay, that was my mistake. So this one I'm going to turn into black, and this one is the one that we promoted. So this, in fact, is 3d10. Okay. Okay. So we have electron promotion being shown here. Through a box diagram. So a lot of these box diagrams can be useful for showing certain patterns that would take us too long to do if we had to draw a quantum mechanic model, and your electron configurations don't show enough detail in terms of what the electrons are doing. Now, chemists often find this to be quite tedious, okay, because you have to draw a box all the time, and then you have to draw arrows. There is an alternate, okay? So instead of drawing boxes, some people opt for drawing circles instead, okay? And instead of arrows, they put lines like this. This would mean 1s1, okay? If you have 2 electrons in that orbital, this would be 1s2. So instead of boxes, they use circles. Some use circles. The only problem with this is that if you're drawing p orbitals, okay, you have to make sure that the circles connect with each other, right? So if you did something like this, this would be 2p3. Okay, this would not be 2p3. There's a gap in between each of these. If you draw it like this, you're telling me that you have individual s orbitals, not a p orbital. So sometimes I do actually prefer the box, okay, because it's way easier to see, especially even if you are drawing it quickly, you can tell the difference between the p's and the s's. And I find that when you use this alternate method of showing the orbitals, okay, you just got to be very careful that they are stuck together and there's no space in between. But all that is up to you in terms of which shape to draw it. Excuse me. Just remember the 3 rules that we talked about earlier: Aufbau's principle, Pauli's exclusion principle, and Hund's rule, because those 3 rules govern how we fill electrons into their orbitals properly. All right, that's all for me. See you guys next time.